Today we're on page 6 of the Chapter 14 AP Chemistry packet. We're going to be finding the pH and percent hydrolysis of a weak base from the Kb. This is analogous to what we did with the acids and the Ka. And instead of writing dissociation right here, we write hydrolysis because bases are not going to dissociate. They're going to react with water to make the hydroxide. We'll take an example of NH3, which is ammonia, which is a weak base. You'll notice that this does not have OH minuses, so it's not going to give you OHs like an Arrhenius base would, but it's going to act like a Bronsted-Lowry base because it's going to take an H from water to make ammonium, and it's going to leave behind from the water the OH minus, which will consequently make the solution more basic. So let's do our ice chart. For this, we're going to write ICE. They're telling us that the concentration is 0.1 molar. Now you don't have to worry about this because it's a liquid, so we'll just cross it off. This is a 0 and a 0, so you're going to shift to the right. So minus x plus x plus x. So you're going to have 0.1 minus x, x, and x. And now, of course, we're going to set this equal to the Kb. The Kb is the same setup as the Ka, except we're not going to put the water in because, again, it's a liquid. So the Kb, in general, is going to be the concentration of NH4 plus times the concentration of OH minus divided by the concentration of NH3 at equilibrium. So we're telling you that the Kb is 1.8 10 to the minus fifth. So 1.8 times 10 to the minus fifth equals x times x over 0.1 minus x. Again, we're going to note that this is very small. 10 to the minus fifth is pretty much the borderline of small. So we're going to ignore this because when you shift to the right in a reaction that favors reactants so much, that this x right here is insignificant when you subtract it from a 0.1. When you do all the math for this, you're going to find out that x equals 0.0013, which looks familiar because this was the exact same answer we got with acetic acid, because acetic acid happens to have a Ka that is 1.8 10 to the minus fifth, and ammonia happens to have a Kb, which is also 1.8 10 to the minus fifth, which it just so happens that those both have the same number, but they're completely not related, really. They just happen to be the same number. So this is going to come out to be a 0.0013 molar for this. This is also going to be a 0.0013 molar for that at equilibrium. And this, when you do the math, is going to be 0.0987 molar. All right, so now what we want to do is we want to find the percent hydrolysis. That's the same calculation as percent dissociation, but you can't call it dissociation because it's not dissociating, it's reacting with water. So that's going to be your x, again, over your original. So it's going to be your 0.0013 over your 0.10 times 100, which gives you a 1.3% hydrolysis. It's the exact same calculations we did with the acids, except this is a base. Now we're going to get the pH. The easy way, in my opinion, to get the pH is simply to get the pOH first and subtract from 14. So the pOH is going to be the negative log of the OH minus, because we already have the OH minus. It's right over here. So why not just use that? So negative log of 0.0013, that's going to equal 2.89. But remember, first 2 sig fig, secondly, this is only pOH, not pH. So we have to take 14 minus 2.89, and that's going to give us 11.11, and that's going to be our pH of the solution. Of course, the other option you had was to convert OH, and not convert, but use 10 to the minus 14th divided by this to get the H, then take the negative log. It's just a little extra work. You would still get 11.11. as your final answer. Okay, now we're going to move on to what happens if you have a mixture of strong and weak acids in the same beaker. So we're going to mix two acids. We're going to mix the strong acid HCl and the weak acid HClO, which is hypochlorous acid. Okay, whenever you're going to do any kind of problem when you're mixing two acids or two bases together, you always start with the strongest one. So start with the strongest one. In this case, the strongest one is a strong, but it's possible you could have two weak ones. You still start with the strongest acid. Okay? So when we start with the HCl, that one's easy, because if I draw a quick picture for this, you'll see that HCl is 100% dissociation versus HClO, draw a little bigger so we could fit it, is mostly going to stay together. All right, mostly stay together. Then you're going to have a little bit of H plus and a little bit of hypochlorite. Just a little, but mostly HClO. So the point is, what happens when we mix these two in one big beaker? What's going to happen? What's the pH really is what we want to find. Okay, so we'll start with the strong one. You know that if you have a 0.1 molar HCl, and this was 0.2 molar originally. Okay, originally, if this is 0.1 molar HCl and this is 0.2 molar HClO, this is just going to translate into 0.1 molar H plus because it's a strong. It's going to 100% break apart. So no matter how much of the acid you have, that's exactly how much H plus you have and exactly how much Cl minus you have. So I'm going to write the Cl minus here as well. It's not going to be pertinent to the pH, but I'm just going to write it so you remember. Okay, so now we did the strong. Now what we want to do is we want to do the weak. So start with the strongest, then do weak. Then do the weaker one. Whenever you have a weak acid, you always have to do ice. So here we go. HClO will dissociate into H plus and ClO minus. You're starting in your initial with 0.2 molar. This is again, now this is going to be tricky. You have to copy down anything from the strong into the initial of the weak. So this is the starting amount of the H plus, 0.10 molar, and then this is going to be 0 because we haven't dissociated the weak yet. So an analogy would be like we're taking little snapshots, okay? So you put this together and it all goes together, you know, in fractions of a second. But we're going to take little snapshots of time. The first snapshot is going to be this breaking apart 100%. So this breaks apart 100%, and we got 0.1 H plus, 0.1 Cl minus. Then the next snapshot after this breaks apart is this breaking apart. So this already broke apart. We already got the H pluses. We got to copy that down over here because they're already floating around from the HCl before the HClO even starts to break apart. So now the HClO will break apart, but not as much, because according to Le Chatelier, if you increase the concentration of a product, you're going to shift equilibrium to the left. Now this one has to shift to the right to make some of this, but it's not going to shift as much as if this were a 0. So if this were 0, this would shift more, but because you already have some of this, it's going to shift less than it would before. It's called a common ion effect. All right, I'll write that down here just so you've seen it. The common ion effect. Because they have a common ion, namely H plus, in both of them, this weak one is not going to dissociate as much. Okay, so we're going to fill in our change line. It's still going to follow stoichiometry, so minus x plus x plus x. So this is going to be 0.2 minus x and 0.1 plus x and x. And we're going to set this equal to the Ka. So K is going to be products over reactants. I'm just going to put them straight in here. So products, 0.1 plus x times x, 0.2 minus x. The Ka was given as 3.5 times 10 to the minus 8. Now that's nice because it's so small. It allows us to ignore this x and ignore this x, which makes our calculations way easier. So now we're going to find out that x, after all this math, comes out to be 7.0 times 10 to the minus 8th. And this is guaranteed to follow the 5% rule. Okay, I'll just write 5%. If you just look at this, negative 1/8 compared to a 0.1 or a 0.2, that's just orders of magnitude less than 5%. So we're good. Okay, so that's my x. So now I'm going to write these in here. I'll use a different color so we can see it. So 7.0 times 10 to the minus 8th molar is x. If you try to subtract this from 0.2, it's not going to do anything. So that's going to be 0.2. And then if you add it to 0.1 again, it's not going to do anything. So you could see that these are the final concentrations. If you wanted, you could do a double check and it would work out. If you took this to the first times this to the first over that to the first, you would get the same Ka, 3.5 10 to the minus 8th. All right, now we want to find the pH. So the pH is equal to negative log of H plus. And that's going to equal the negative log of 0.1. which is equal to a pH of 1.00. Remember, that's 2 sig figs. And then after all that work, you should be looking at this and saying, wait a minute. We didn't even have to do the ice to find the pH because the H was already 0.1, and then I put it over here, and then I ignored the X, and I still got 0.1, and you're right. So what we discover is when you mix a strong acid and a weak acid, and you only care about the H pluses, if it's a weak enough acid, like a minus 1/8 over here, the H plus from the acid is going to be insignificant. So if they only ask you for the pH, you could simply just use the strong one and be done. Okay, but chances are they want you to do this ice calculation, so they're also going to ask you for something like what is the concentration of the hypochlorite in the solution. So that you would have to do the ice to get this answer right here. And so when you look at this big beaker, you're going to have a bunch of H pluses, a bunch of Cl minuses, a tiny extra bit of H plus that's not going to matter compared to this, but you will also have a tiny little bit of ClO minus coming from the HClO as well.